Our universe holds a secret that defies the laws of physics. Entire galaxies spin so fast they should fly apart, yet they remain perfectly intact. This is the mystery of rotating galaxies that should not spin that way, a cosmic puzzle that directly challenges our core understanding of gravity. By the end of this journey, you will see the cosmos through the eyes of a detective, uncovering the clues behind one of science's greatest enigmas. We will explore an invisible cosmic glue and a potential rewrite of physics itself. What force holds these spinning giants together against all odds? Vera Rubin peered into the data from the Andromeda Galaxy and found a puzzle that refused to fit. She expected to see a graceful slowdown, a celestial dance where stars on the outer fringes moved more sluggishly than those near the bright core. This is how our own solar system behaves, with distant Pluto crawling along its orbit while inner Mercury races around the Sun. But the galaxies told a different story. Stars far from the luminous center, out in the dim, sparse outskirts, were hurtling around at the same tremendous speed as their inner cousins. The graph of their velocity did not fall away into a slope. It stayed flat, a straight line of defiance against established physics. According to the laws of gravity as we knew them, this should have been impossible. There simply was not enough visible matter, not enough stars and gas, to generate the gravitational force required to whip those outer stars around so quickly. The galaxies were spinning so fast they should have flown apart, scattering stars into the void. Yet they held together perfectly intact. Rubin's work was the first undeniable clue that we were missing most of the universe. The majority of the cosmic glue holding everything together was completely invisible, a hidden force that we could not see, but whose gravitational pull was unmistakable. This discovery launched the greatest treasure hunt in the history of science, a search for the missing ingredient of the cosmos. This flat line on the graph is the ghost in the machine, a direct challenge written in starlight. To truly grasp its defiance, picture our own solar system. The Sun, a colossal anchor of mass at the center, dictates the orbits of all the planets. Mercury, close in, feels the Sun's immense gravitational pull and whips around at a blistering speed. But distant Neptune, far out in the cold, moves at a leisurely crawl. Its orbital path is a slow, wide arc. This is the predictable behavior we expect from gravity, a clear and steady decline in speed with distance. We call this pattern a Keplerian decline, and for centuries it was the unshakable rule for how objects orbit a central mass. This is the curve astronomers expected to see when they charted the stars in a galaxy. They predicted a steep climb in speed near the bright, dense core, followed by that same familiar, graceful fall. But the universe had a different answer. The data did not fall, it stayed flat. Stars at the very edge of the galaxy, where light is faint and matter seems sparse, were racing along at the same incredible velocity as the stars near the center. It was as if every car on a vast, sprawling highway, from the downtown exit to the furthest rural stretch, was somehow traveling at exactly 100 miles per hour. This was the rotation curve anomaly, a universal signature of a hidden reality. The visible galaxy, the beautiful spiral of stars and gas we see in telescopes, is merely the tip of a cosmic iceberg. The flat rotation curve is the invisible proof of a massive, unseen halo, a vast sphere of something enveloping the entire galaxy, its gravitational grip reaching out to whip the outer stars into a frenzied, impossible dance. This discrepancy is not a small error. It is a fundamental problem that simple adjustments to known physics could not solve. The ghostly hand was real, and its grasp was everywhere. This conflict between what we see and what the laws of physics demand did not begin with Vera Rubin. Its roots stretch back centuries to the very foundations of our understanding of motion and gravity. Isaac Newton gave us a set of rules that seemed to govern the cosmos, laws of motion and universal gravitation that perfectly predicted the elliptical dance of the planets around our sun. Later refined by Johannes Kepler, these orbital mechanics became a pillar of celestial certainty. For generations, these rules worked flawlessly. They guided our spacecraft and explained the clockwork of our solar system. So when astronomers naturally applied these same, trusted laws to the vast structures of entire galaxies, they had every reason to expect a familiar pattern, that graceful decline in orbital speed. The prediction was clear and confident. The universe, however, had other plans. The refusal of galaxies to follow this ancient rule pointed to a chasm in our knowledge. Either our understanding of gravity itself was fundamentally incomplete on cosmic scales, or the universe was filled with something we could not see. Vera Rubin's meticulous work on galaxy rotation was the crucial, undeniable proof that forced this dilemma into the spotlight. Yet the first whispers of this mystery emerged decades earlier. In the 1930s, a brilliant and often overlooked astronomer named Fritz Zwicky was studying the Coma Cluster, a vast gathering of galaxies. By applying a principle called the virial theorem, which relates the kinetic energy of a system to its potential energy, he calculated how much mass should be present to hold the cluster together gravitationally. The result was shocking. The visible mass of all the stars and gas in those galaxies was nowhere near enough. The cluster should have flown apart. Zwicky inferred the presence of what he called Dunkelmaterie, dark matter, an invisible substance providing the missing gravitational glue. At the time, his idea was largely dismissed, but this historical progression reveals a profound truth. The mystery of the spinning galaxies was not a single, sudden discovery. It was a gradual, dawning realization, a series of clues collected over generations that slowly eroded our classical certainty. The journey from Newton's orderly clockwork to our modern cosmic puzzle sets the stage for a revolution, forcing us to question the very fabric of the universe we thought we knew. This invisible cosmic glue, the prime suspect in our galactic mystery, is known as dark matter. Think of it as a ghostly scaffold, a vast and unseen structure that holds the visible universe together. Unlike the atoms that make up you, me, and every star we see, dark matter is something entirely different. It does not shine, absorb, or reflect any form of light. Our most powerful telescopes from Hubble to James Webb look directly through it as if it were not even there, yet it possesses mass, and with mass comes gravity. This is how it betrays its presence, through its relentless gravitational pull. The leading theory suggests this mysterious substance forms an immense, spherical halo around each galaxy, a cloud of invisible particles that extends far beyond the last visible star. It is this extra mass, this hidden anchor, that generates the powerful gravity needed to keep those outer stars whipping around at impossible speeds. Without this dark matter halo, a galaxy would simply fling itself apart. The sheer amount required to produce this effect is staggering. Scientists calculate that dark matter makes up roughly 27% of everything in the universe. The ordinary matter we know and love, the stuff of planets and people, accounts for a paltry 5%. For every single galaxy we admire in the night sky, there is 5 times more dark matter holding it together than the shining stars we actually see. The evidence for this ghostly presence extends far beyond spinning galaxies. When astronomers look at massive galaxy clusters, they sometimes see distant, distorted galaxies in the background. This is because the immense gravity of the cluster's dark matter is bending the very fabric of space-time, acting like a giant lens that warps the light from objects behind it. This phenomenon, called gravitational lensing, provides another independent line of proof for the unseen mass. Dark matter also dictated how the cosmic web formed, guiding the flow of gas and dust into the vast filaments and voids we observe today. So while we cannot see it, touch it, or bottle it, the gravitational fingerprint of dark matter is written across the entire cosmos. It is the leading explanation, the best fit for the clues we have gathered. Yet its fundamental nature remains one of the most profound and elusive quests in all of science. We know what it does, but we still do not know what it is. But what if our cosmic detective story has been looking for the wrong suspect? What if the culprit is not a missing substance, but a fundamental error in our most trusted law? This radical idea challenges the very premise of dark matter. It proposes that Isaac Newton's laws of gravity, while perfect for our solar system, simply break down in the vast, faint outskirts of galaxies. This alternative is known as modified Newtonian dynamics, or MOND, a theory born from the mind of physicist Mordechai Milgram in the 1980s. Milgram's insight was to focus on acceleration, not mass. He proposed that when the gravitational pull becomes incredibly weak, as it does for a star far from a galaxy's bright center, Newton's familiar equations no longer apply. Instead, a new rule takes over, one where gravity gets a subtle boost under these extreme low acceleration conditions. To understand this, think of driving a car. On a normal city street, pressing the gas pedal gives you a predictable increase in speed. This is like gravity in our solar system. It behaves as expected. But MOND suggests that on a vast, empty highway, the car's response to the pedal changes. A tiny press on the accelerator might suddenly provide a much stronger push than anticipated. In the galactic outskirts, this modified gravity acts as an invisible hand, providing the extra pull needed to keep those outer stars moving fast, perfectly explaining the flat rotation curve without a single particle of dark matter. For many spiral galaxies, MOND predictions are stunningly accurate. Its proponents argue it is a more elegant and direct solution, cutting out the need to invent an entire universe of invisible stuff that, despite decades of searching, we have never directly caught. Yet for all its success with individual galaxies, MOND faces a monumental challenge of its own. It struggles to explain what we see when entire galaxy clusters, each containing thousands of galaxies, collide with one another. Observations of one such colossal crash, the Bullet Cluster, show that most of the mass mapped through gravitational lensing is separated from the visible gas. This suggests the mass is carried by something that does not interact, something that sails right through the collision, just like dark matter would. For MOND to survive, it requires complex additions, making it less simple and elegant, so we are left with two compelling yet incomplete explanations. One fills the cosmos with an unseen ghost, the other rewrites the rules of physics itself. The mystery of the spinning galaxies has forced us into a corner where both answers seem equally profound and equally unsettling. Einstein's vision of gravity gives us a way to see the invisible. He described space and time as a flexible fabric, a cosmic sheet that curves and dimples under the weight of any object with mass. Light traveling across this warped fabric does not move in a perfectly straight line. It follows the curves, bending like a car tracing a winding road. This effect is gravitational lensing, and it has become one of our most powerful tools for weighing the cosmos. When astronomers train their telescopes on a massive galaxy cluster, they sometimes see a strange and beautiful sight. Distant galaxies behind the cluster appear not as sharp pinpricks, but as stretched, smeared, and twisted arcs of light. It is as if they are looking through a giant, rippled piece of glass. This distortion happens because the immense gravity of the foreground cluster is bending the very paths of the light rays coming from those faraway galaxies. By carefully measuring this distortion, scientists can create a map of the cluster's total gravitational pull and therefore its total mass. The results are always the same. The amount of mass required to create such dramatic lensing is enormous, far greater than the combined mass of every star, every planet, and every cloud of glowing gas we can see in the cluster. The visible matter simply does not add up. This missing mass, revealed only by its gravity, has a specific distribution. It forms a vast, smooth halo that permeates the entire cluster, exactly where we would expect the dark matter to be. This cosmic scale provides a check, an independent line of evidence that points to the same conclusion. The same invisible substance that whips individual galaxies into a frenzied spin is also sculpting the light from the deep universe, its ghostly hand revealed in the warped images of distant galaxies. The Bullet Cluster offers a cosmic crime scene where the evidence speaks for itself. This system is not a single object, but the spectacular aftermath of two galaxy clusters that have violently smashed into one another. Such a collision unleashes forces beyond comprehension, and it is here that the two main suspects in our mystery, dark matter and modified gravity, face their most difficult test. When these immense clusters collide, their different components behave in starkly different ways. The galaxies themselves, vast collections of stars, are mostly empty space. They pass by each other like swarms of ghosts, largely unaffected. The majority of the ordinary, visible matter, however, exists as immense clouds of superheated gas that fill the space between the galaxies. During the collision, this gas slams together. It experiences a powerful drag, like a hand moving through thick syrup, and it slows down dramatically, piling up in the central region between the two clusters. If all matter were ordinary and visible, the bulk of the mass should be right there, trapped in that pile of hot gas. But when astronomers used gravitational lensing to map the true distribution of mass, they found something astonishing. The map revealed that most of the mass was not in the center with the gas. Instead, it had sailed clean through the collision site, completely unimpeded, and was now located where the galaxies were. This is the smoking gun. The dominant form of mass in the universe is something that does not interact with the gassy sludge of ordinary matter. It feels gravity, but it does not feel friction, pressure, or any electromagnetic force. It is, by every definition, dark and collisionless. For theories like MOND, which rely on tweaking the laws of gravity, this observation presents a monumental hurdle. How could a modification of gravity explain why the gravitational pull itself has become separated from the visible matter? The Bullet Cluster stands as a powerful testament, suggesting that the ghostly scaffold of dark matter is not just a mathematical fix, but a real, physical substance that moves through the cosmos and through itself as if it were not even there. An elegant solution for spinning galaxies begins to fray at the edges of the cosmos. Its modifications to gravity, so effective on the scale of a single spiral, struggle to explain the universe in its infancy. One of the most powerful snapshots from the dawn of time is the cosmic microwave background, the faint, cold glow left over from the Big Bang. This radiation is not perfectly smooth. It holds a specific pattern of hot and cold spots, a frozen imprint of the young universe's lumpy structure. For decades, supercomputer simulations have shown that these precise patterns emerge only if a significant amount of dark matter is present from the very beginning. The gravitational pull of this unseen matter is essential for sculpting those early ripples into the universe we see today. When theorists try to replicate this cosmic blueprint using only MOND rules, the pattern does not match. The pieces of the puzzle simply do not fit. The same problem appears when we look at the largest structures in existence. The cosmic web, that vast network of galaxy filaments and empty voids, took billions of years to form under the relentless pull of gravity. In a universe governed purely by MOND, this process would have unfolded far too slowly. The web we observe, with its dense clusters and sprawling filaments, would not have had enough time to assemble itself. To rescue the theory, many proponents have had to introduce a new ingredient, something like sterile neutrinos, a type of particle that does not interact with ordinary matter. Yet this begins to sound very familiar. It is, in essence, a form of dark matter. The very substance MOND was created to avoid must be invited back in to make the larger picture work. Even on smaller scales, there are puzzles. Some faint dwarf galaxies orbiting our own Milky Way possess a gravitational strength that seems to demand more mass than MOND can easily provide without careful, specific adjustments. So we are faced with a profound trade-off. Does the elegance of modifying gravity on galactic scales outweigh its inability to stand alone across the entire cosmos? The choice is not between a perfect theory and a flawed one, but between two different sets of mysteries, each with its own compelling evidence and its own glaring gaps. So the hunt for a ghost begins. If dark matter is real, what substance could possibly constitute 27% of the universe yet remain utterly invisible to us? The prime suspect is a hypothetical particle known as a WIMP, an acronym for Weakly Interacting Massive Particle. Imagine a cosmic phantom, a particle so aloof it barely acknowledges the existence of ordinary matter. It would have mass and therefore gravity, but it would ignore both light and the strong nuclear force that binds atoms together. Its only other potential interaction would be through the weak nuclear force, the same force responsible for radioactive decay. This profound shyness is what makes WIMP so elusive. To catch one, scientists have built the most quiet, shielded laboratories on Earth. Places like the LUX Zeppelin and Xenon NT experiments are located deep underground, in old mines or beneath mountains, where thousands of feet of rock block out the constant rain of cosmic rays. At their heart are enormous vats of ultra-pure liquid xenon, chilled to extreme temperatures. The entire setup is a trap of exquisite sensitivity, waiting in the dark for the almost unimaginably rare event. The hope is that once every long while, a single WIMP from the vast halo enveloping our galaxy will drift through the tank and, against all odds, bump directly into the nucleus of a xenon atom. That tiny collision would create a faint flash of light and a wisp of electric charge, a signature that could finally announce the ghost's presence. But after decades of searching with ever more sensitive detectors, that definitive signal has not come. The WIMP remain at large. This silence has forced the hunt to broaden. In space, telescopes like the Fermi Gamma Ray Space Telescope scan the heavens for indirect evidence. They search for specific patterns of gamma rays, the most energetic form of light, which could be produced if two WIMP were to collide and annihilate each other in the dense dark matter halos around galaxies. Still, the sky offers no clear answer. With the leading candidate evading capture, physicists are increasingly turning to other, more exotic possibilities. Perhaps dark matter is made of actions, particles so lightweight and numerous they could behave like a coherent wave flowing through the cosmos. Or maybe the answer lies in the very first moments of the Big Bang, with the creation of countless primordial black holes, ancient relics so small and dark they would be virtually impossible to find. Each of these ideas is a different path in the same great hunt, a search for the fundamental particle that holds our universe together. The mystery of the spinning galaxies has led us here, to this profound and frustrating frontier, where we know the ghost's handiwork but have yet to see its face. Our cosmic crime scene now shifts from the telescope to the supercomputer. To test the dark matter hypothesis, scientists have attempted the ultimate reconstruction, building entire universes from scratch inside a machine. They start with a near-perfect soup, a universe just moments after the Big Bang, almost uniform but for the tiniest of quantum ripples. Then they set the laws of physics in motion and let time fly forward at a blistering digital pace. The results are unequivocal. When these simulations include a substantial amount of cold dark matter, something remarkable happens. That smooth primordial soup, under the relentless pull of gravity from the unseen dark matter, begins to clump. Vast, invisible filaments emerge, weaving a cosmic web across billions of light-years. At the intersections of these dark threads, matter pools into dense halos. It is here, within these gravitational wells sculpted by the invisible, that ordinary matter, the gas and dust we are made of, is finally drawn in. This gas cools, condenses, and ignites into the first stars, eventually assembling the brilliant galaxies we recognize. This entire process, from a smooth beginning to a structured end, unfolds naturally within the observed age of our universe, 13.8 billion years. The most successful of these digital universes is known as the Lambda Cold Dark Matter model. Now run the simulation again, but this time remove the dark matter. The outcome is a universe that looks nothing like our own. Without that dark scaffolding to guide and accelerate the process, the growth of structure is stunted and slow. The beautiful, intricate cosmic web fails to form in time. The galaxies that do emerge are too few, too small, and scattered in a pattern that does not match the one painted across our real night sky. This digital evidence is profound. It suggests that dark matter is not merely a fix for spinning galaxies, but the fundamental architectural blueprint for everything we see. The success of these simulations in recreating the entire large-scale structure of the cosmos provides one of the most compelling, albeit indirect, arguments that this invisible ingredient is absolutely essential to our cosmic recipe. The light from a distant galaxy holds a hidden signature of its motion. To measure the spin of these colossal structures, astronomers perform a kind of celestial forensics, decoding subtle shifts in the very color of starlight. The key technique is spectroscopy, which breaks light into its constituent rainbow of colors, revealing a unique fingerprint for every element in the cosmos. Within that rainbow, specific, expected colors appear as sharp lines. The magic happens when those lines are not where they should be. If a star or a cloud of gas is moving toward us, its light waves are compressed, shifting the entire fingerprint slightly toward the blue end of the spectrum. If it is moving away, the light is stretched, shifting the fingerprint toward red. This is the Doppler effect in action, the same principle that makes a siren's pitch drop as a police car speeds past you. By pointing a powerful telescope at different sections of a spiral galaxy, from its bright core to its dim, wispy edges, astronomers can measure these tiny red and blue shifts for thousands of points of light. They are not just looking at the stars themselves. The most crucial measurements often come from vast, cold clouds of neutral hydrogen gas that permeate a galaxy's disk. Radio telescopes are uniquely suited for this task. They are tuned to listen for a very specific whisper from space, the 21-centimeter line, a faint radio signal that hydrogen atoms naturally emit. This signal is a perfect tracer, because this cold hydrogen extends far beyond a galaxy's visible starlight. It allows scientists to map the rotation curve deep into the otherwise dark and seemingly empty outskirts. The process is meticulous, a pixel-by-pixel construction of a galaxy's velocity map. The result is that now famous graph, a line that stubbornly refuses to fall, a plot of speed against distance that revealed a universe filled with ghosts. This precise measurement, repeated for galaxy after galaxy, is the unshakable data point that forced us to choose between an invisible cosmos and a broken law. The mystery deepens when we realize that galaxies do not all spin the same way. Our focus on spiral galaxies with their elegant flat rotation curves is only one part of a much more complex story. The universe presents us with a whole zoo of galactic shapes, each with its own internal logic and its own gravitational secrets. Elliptical galaxies, for instance, are vast, fuzzy clouds of ancient stars that lack a distinct disk. They do not spin in an orderly fashion like a pinwheel. Instead, their stars swarm in a chaotic, random dance, moving in all directions like a hive of angry bees. This makes their internal motions incredibly difficult to map and measure, obscuring the clear signal of a rotation curve. Yet even their chaotic energy hints at a gravitational anchor, a hidden mass holding the entire swarm together against the centrifugal force of their motion. Then there are the dwarf galaxies, small, faint satellites that orbit giants like our Milky Way. Some of these diminutive systems possess a startling ferocity. Their stars move with a surprisingly high velocity dispersion, meaning they are zipping around in random directions at speeds that their meager visible mass could never contain. These tiny galaxies appear to be almost pure dark matter, with the few stars we see merely floating in an immense, invisible sea of the stuff. But the plot thickens even further with the discovery of a truly bizarre class of objects, ultra-diffuse galaxies. These are ghostly giants, as wide as the Milky Way, but with so few stars they are nearly transparent. Logic would suggest that such faint, wispy structures must be dominated by dark matter to hold themselves together. Yet for some of these UDGS, the measurements reveal the opposite. Their stars move with a lethargy that matches their faint glow, suggesting there is almost no dark matter present at all. They are cosmic paradoxes, vast yet light, challenging the very idea that dark matter is a universal and mandatory ingredient. This incredible diversity complicates our search for a single, neat answer. It suggests the cosmic recipe for a galaxy is not fixed. The relationship between the light we see and the gravity we feel might be a flexible partnership, one that can produce a dark matter-dominated dwarf, a seemingly empty ghost, and everything in between. Perhaps the answer has been hiding in plain sight, woven into the very fabric of the galaxies we can see. This line of inquiry asks if ordinary matter, the stuff of stars and supernova, could be orchestrating a more complex gravitational dance than we first imagined. We call this baryonic feedback, and it is the universe's own dramatic display of cause and effect. At the heart of every galaxy, titanic forces are constantly at work. When massive stars reach the end of their lives, they do not fade quietly. They explode as supernova, blasting out shockwaves that heat surrounding gas to millions of degrees and physically push it far out into the galactic halo. On an even grander scale, supermassive black holes at the centers of galaxies can become active galactic nuclei, swallowing matter, and then belching out colossal jets of energy that ripple through interstellar space. This feedback is like a cosmic regulator, a series of powerful engines that can stir, heat, and even eject vast reservoirs of normal matter. In the most advanced supercomputer simulations, this chaotic ballet of baryonic physics does leave a subtle mark. It can slightly reshape the inner regions of a galaxy's rotation curve, creating small wiggles and dips that reflect the movement of this churning, energized gas. For a moment, it seems we might be closing the case with the evidence right in front of us. Yet this promising lead quickly hits a wall. The influence of these stellar and black hole engines, for all its ferocity, is ultimately local. It is a storm contained within the inner galaxy. When we look to the outer, dark reaches, to those distant stars hurtling along at inexplicable speeds, the math simply fails. The gravitational pull required to keep those stars on their flat, fast trajectories is orders of magnitude stronger than anything the combined push and pull of ordinary matter could ever generate. Baryonic feedback might sculpt the fine details, but it cannot lay the foundation for the entire structure. It is the decorative icing on a cake that must be made of something else entirely, something whose gravitational signature is both immense and invisible. Our next chapter in this cosmic investigation is being written by a new generation of eyes on the sky. These are not mere upgrades, but revolutionary instruments designed to probe the dark matter mystery with a precision that was once the stuff of dreams. The James Webb Space Telescope acts as a time machine, gazing back to an era when the first galaxies were assembling. By studying these infant structures, astronomers can test a fundamental prediction. Did the very first stars and galaxies also spin with that impossible velocity, their outer regions already gripped by dark matter's unseen hand? Or does the story of this cosmic glue begin later in the universe's history? Webb's deep infrared vision is peeling back the layers of time to find out. Back in the modern universe, ground-based giants are preparing for an equally daunting task. The extremely large telescope being built on a mountaintop in Chile will be a colossal eye on the cosmos. Its primary mirror, spanning nearly 40 meters, will collect starlight with breathtaking clarity. This power will be used to create exquisitely detailed spectroscopic maps of galaxies closer to home. It will measure the motions of individual star clusters and even trace the faintest wisps of gas with unprecedented accuracy. These high-resolution kinematic maps could reveal subtle twists and turns in a galaxy's rotation, tiny deviations that might finally tip the scales decisively toward either the particle nature of dark matter or a specific modification of gravity. The final piece of this observational trinity takes a wider view. The Vera Rubin Observatory, with its enormous 3.2 billion pixel camera, will embark on a decade-long cinematic survey of the entire southern sky. Night after night, it will capture the universe in motion, discovering millions of previously unknown galaxies and automatically measuring their rotation curves. This will not be about the detailed study of a single object, but about amassing a statistical powerhouse of data. By analyzing the rotations of countless galaxies of all shapes, sizes, and ages, scientists will see the broader patterns emerge. They will be able to ask with immense confidence how universal the dark matter signature truly is. These observatories, working in concert, offer our best chance yet to move from circumstantial evidence to a definitive verdict. They are the keys to a new era of discovery, where the ghost in the cosmic machine may finally have to show itself. This mystery ultimately forces us to confront a question that is as much about philosophy as it is about physics. Are we truly prepared to accept that 85% of all matter in the cosmos is an invisible, intangible ghost, something we can only infer by its gravitational shadow? Or does it feel more reasonable, more elegant, to revise a law of gravity that has been our unwavering guide since the time of Isaac Newton? This is the core dilemma, a battle between two different kinds of simplicity. On one hand, you have the dark matter hypothesis, which introduces a vast new substance to explain the observations. On the other, you have modified gravity, which changes the rules of the game itself. Which path is truly simpler? This is a classic application of Occam's razor, the philosophical principle that suggests the explanation with the fewest assumptions is usually the best. But here, the definition of simple is deeply blurred. Is it simpler to fill the universe with a particle we have never seen, or to rewrite the fundamental laws that have governed our understanding of motion for over 300 years? There is no easy answer because both choices lead to profound and unsettling consequences. This entire journey, from Vera Rubin's flat line to the bullet cluster's smoking gun, serves as a powerful testament to what science really is. It is not a dusty book of settled facts. It is a living, breathing, and often messy process of relentless questioning. It is a system built on the humbling idea that our most cherished theories are always provisional, always subject to being upended by the next unexpected piece of evidence from the cosmos. The spinning galaxies that should not exist have not given us a final answer, but they have given us something perhaps more valuable, a permanent reminder of our own ignorance and the thrilling, endless frontier of discovery that lies ahead. Our galactic mystery connects to an even deeper cosmic rift. Across the universe, astronomers are measuring two different expansion rates, a discrepancy so stubborn it has earned its own name, the Hubble tension. When we use distant relics from the early universe, like the cosmic microwave background, to calculate how fast space is stretching, we get one number. Yet when we measure the expansion directly using nearby stars and supernova, we get a significantly faster result. These two methods should agree, but they do not. This is not a small error in measurement. It is a fundamental clash of observations, and some scientists are beginning to wonder if it is related to the forces twisting galaxies. Could the same unknown physics that provides the extra pull to spin galaxies also be giving the cosmos an unexpected push, accelerating its expansion in a new way? Perhaps a dynamic form of dark energy or a new property of dark matter itself is at work on both the vast scales of the cosmos and within the confines of individual galaxies. This idea remains highly speculative, a thread of possibility connecting two of astronomy's greatest puzzles, yet its mere existence sends a powerful message. The lambda-cold dark matter model, our standard cosmic recipe, has been phenomenally successful at describing the universe from its largest structures to its ancient origins. But these persistent tensions, the spinning that should not be and the expansion that does not match, are like hairline fractures in a beautiful sculpture. They hint that our model, for all its power, is an incomplete picture of reality. We may be on the verge of discovering something far more complex and wondrous, a new layer of physics that governs both the grand sweep of cosmic history and the intimate dance of the stars. Could the dark heart of a galaxy hold the answer? At the center of most large galaxies, including our own Milky Way, lies a supermassive black hole, a gravitational monster with the mass of millions or even billions of suns. Its presence is undeniable, its power to shred stars and warp spacetime absolute. Yet when we put these colossal objects on the cosmic scale, they are surprisingly lightweight. The mass of even the most gigantic central black hole is a mere fraction, less than 1%, of the total mass of its host galaxy. Its gravitational grip is fierce but intensely local, dictating the orbits of nearby stars while fading to insignificance in the galaxy's vast outer realms. This simple math extinguishes any hope that these known beasts are the hidden force behind the flat rotation curves. Their pull is a whisper against the galactic roar of dark matter. But what if the connection is more subtle, or the nature of the darkness itself is tied to black holes? Some theorists explore a fascinating possibility that dark matter is not a sea of exotic particles, but a cosmic fog of ancient black holes. These would not be the stellar remnants we know, but primordial black holes forged in the unimaginable density of the Big Bang's first second. Trillions of these faint, planet-sized relics could be drifting through every galaxy, their collective mass forming the invisible halo. While an elegant idea, searches for these primordial objects through their gravitational lensing effects have so far come up mostly empty, suggesting they cannot make up the bulk of the dark matter. A more nuanced idea involves the interaction between the known central black hole and the unseen halo. The intense gravity of the supermassive black hole could act like a cosmic magnet, pulling the surrounding dark matter into an ultra-dense spike at the very core of the galaxy. This dense concentration would leave a subtle imprint on the inner rotation curve and might even influence the rate at which dark matter particles annihilate each other. So while the central black hole is not the master of the galactic spin, it might be the conductor of a dark orchestra in the inner core, its gravity tuning the distribution and behavior of the true unseen mass. The relationship between the most luminous vacuum in space and the most pervasive darkness remains a vibrant and open question, one where the extremes of physics meet. This cosmic puzzle reaches far beyond the pages of academic journals, igniting a spark of wonder in classrooms and planetariums around the world. The story of Vera Rubin herself is a testament to perseverance, a narrative of a brilliant mind navigating a field that was not always welcoming to women. Her dedication in the face of professional obstacles, leading to a discovery that fundamentally reshaped our cosmic view, provides a powerful and human inspiration for any young person dreaming of a life in science. The mystery she helped uncover is a perfect gateway to understanding how science truly works. Here is a problem where you cannot see the culprit, you cannot touch it or photograph it. Yet, through the elegant application of mathematics and the meticulous gathering of observational clues, you can prove it must be there. This is the scientific method in its most thrilling form, a celestial detective story where logic and evidence are the only tools that can reveal a hidden reality. This is why planetarium shows so often feature spinning galaxies, and why science documentaries return to this topic again and again. It perfectly encapsulates the core of exploration, the moment when observation clashes with expectation, forcing a revolution in thought. By engaging with this grand puzzle, we do more than just hunt for an invisible particle or a new law of physics. We are actively nurturing a vital human trait, a sense of boundless curiosity, and the critical thinking skills needed to navigate an increasingly complex world. The future of science and of society itself depends on this very spirit of inquiry, on the next generation looking up at the stars and daring to ask, what else are we missing? The search for an invisible cosmic substance has forced us to build machines of breathtaking sensitivity. To hunt for dark matter, we cannot simply build a bigger telescope. We must create an environment of perfect quiet, a place shielded from the constant noise of our own world. This demand for silence has pushed engineering to its absolute limits. Detectors like LUX Zeppelin and Xenon NT rely on vats of ultra-pure liquid xenon, chilled to temperatures colder than the void between stars, just creating materials that are pure enough and systems that are stable enough for these experiments is a monumental feat of human ingenuity. The slightest vibration, a stray radioactive decay from the surrounding rock, or even a cosmic ray from the sun, can ruin the entire search. This relentless pursuit of one scientific answer has become a powerful engine for technological progress, spinning off advances that ripple far beyond the lab. The same sophisticated algorithms developed to sift through terabytes of telescope data, searching for the faint gravitational signature of dark matter in millions of galaxies, are now being adapted to analyze complex problems in medicine and finance. These powerful tools for recognizing subtle patterns in a sea of noise are finding new life in machine learning and big data analytics. History shows us that the pursuit of fundamental knowledge, driven by pure curiosity, often yields the most profound and unexpected practical rewards. The entire World Wide Web, the very fabric of our modern digital world, was invented at the CERN laboratory as a tool for particle physicists to share their data. No one at the time was trying to create a global communication network, yet that is precisely what emerged from the quest to understand the building blocks of matter. Investing in the mysteries of the cosmos is not an abstract exercise. It is a direct investment in our own technological future, forcing us to solve impossible problems and, in doing so, pushing the boundaries of what is possible for everyone. These cosmic terms can sometimes blur together, creating a fog of misunderstanding. Let's clear the air on a few crucial points. First, dark matter is not a force of anti-gravity. It does not push or repel. In fact, its gravitational pull is entirely normal and attractive, just like the gravity from a planet or a star. Its only crime is that it pulls with the strength of an invisible giant. This is fundamentally different from dark energy, the true cosmic rebel. Dark energy is the name for the mysterious phenomenon that is causing the expansion of our entire universe to accelerate, an anti-gravitational push on the grandest scale. They are two separate mysteries, two different entries in our cosmic ledger of the unknown. One provides the extra gravitational glue to hold galaxies together, while the other is actively pushing the very fabric of the cosmos apart. The persistence of this galactic puzzle is also not a sign that science is failing. It is the opposite. This is science operating at its absolute best. The entire process is built to identify anomalies, to find the one piece of data that does not fit the established picture. That moment of confusion, that stubborn flat line on a graph, is not an end. It is the most exciting beginning, the spark that ignites a new era of discovery and forces us to dig deeper into the nature of reality itself. This mystery is a feature of the scientific process, not a bug. And finally, the word dark itself. In the language of physics, dark carries no moral weight. It is not a label for something sinister or evil. It is a simple technical term meaning it does not emit, absorb, or reflect any form of light. It is electromagnetically dark, completely transparent to the entire spectrum. By untangling these common confusions, we can see the debate with sharper clarity, appreciating the precise and nuanced challenge that the spinning galaxies have laid at our feet. This galactic mystery cannot be solved by a lone astronomer peering through a telescope. It demands a symphony of expertise, a collaboration that spans the entire scientific landscape. Particle physicists work in deep underground laboratories, dreaming up new particles and building exquisite traps to catch them. Cosmologists run universe-spanning simulations on supercomputers, testing how dark matter shaped the cosmos from its first moments. Astrophysicists meticulously map the rotation of countless galaxies, gathering the raw data that fuels the entire search. And none of this would be possible without computer scientists, who develop the algorithms to sift through mountains of telescope data and model realities we cannot otherwise see. This is the interdisciplinary engine of modern big science. At international conferences and within massive collaborations, these diverse minds converge. A theorist's new idea about an action particle can immediately shape how an observer analyzes a new galactic survey. A surprising result from a deep space telescope can send the simulators back to their digital drawing boards. Each piece of information, from the subatomic to the galactic, is a vital clue that only makes sense when combined with the others. The quest to understand why galaxies spin so fast is a powerful reminder that the universe does not respect the artificial boundaries we draw between scientific fields. The biggest questions require us to pool our knowledge, to see the same problem through a dozen different lenses at once. This collective effort, This shared struggle against the unknown is perhaps our greatest tool in the hunt for cosmic truth. The Triangulum galaxy offers a perfect laboratory to test our cosmic theories. Located a mere 3 million light-years away, this beautiful spiral is one of our closest galactic neighbors, close enough for our telescopes to dissect its motion in extraordinary detail. Radio telescopes have spent countless hours listening to its faint whispers, mapping the distribution of its cold hydrogen gas. The resulting rotation curve is a textbook example of the mystery, a perfectly flat line from its bright core to its most distant, tenuous edges. This flat profile is the undeniable signature, the gravitational fingerprint of something massive and unseen. Astronomers then perform a kind of cosmic accounting. They calculate the total gravitational pull that should be generated by everything they can see, every star, every nebula, every speck of dust. The sum is impressive, but it falls catastrophically short. It cannot possibly account for the speed at which the galaxy's outer regions are spinning. The only logical conclusion is the presence of a vast spherical halo of dark matter, an invisible sphere of influence that envelops the entire luminous galaxy. By subtracting the gravity of the scene from the gravity required by the spin, scientists can even map the rough shape and density of this ghostly halo. In the case of the Triangulum galaxy, this dark shroud extends to at least twice the radius of its visible starlight. This meticulous process, repeated for galaxy after galaxy, transforms an abstract puzzle into a tangible, measurable reality. It demonstrates that the evidence for dark matter is not a single grand argument, but a mountain of data built one careful observation at a time. Our finest tools have come up empty in the face of this cosmic ghost. The most powerful telescopes ever built stare directly through the dark matter halos that we know must be there. Deep underground, vats of liquid xenon wait in perfect silence, yet they have not recorded the unambiguous bump of a dark matter particle. This is not a failure of science, but its very nature. We are pushing at the boundaries of the known, and by definition, the frontier is a place of uncertainty. The theories we have crafted are powerful, yet incomplete. The lambda-cold dark matter model beautifully describes the universe's large-scale structure, but the particle itself remains a phantom. Modified Newtonian dynamics offers an elegant solution for galaxy rotations, but it stumbles when faced with the bullet cluster or the cosmos in its infancy, unable to yet provide a full, relativistic theory that replaces Einstein's gravity on all scales. This state of not knowing is the most exciting place a scientist can be. It means the puzzle is still being solved, the final chapter has not been written. The next great leap could come from anywhere, a single, faint signal from a detector a mile underground, a new, inexplicable pattern in the rotation of a distant galaxy spotted by the James Webb Telescope. Or perhaps a brilliant, unforeseen idea that rewrites the rules from the ground up. To stand at this precipice, to acknowledge the limits of our current understanding, is not an admission of defeat. It is an acceptance of the challenge. It is this very uncertainty that fuels our curiosity, that drives the construction of ever more sensitive instruments and the pursuit of ever more daring ideas. We are living in the middle of a cosmic detective story, and the next clue could break the case wide open at any moment. Solving this cosmic riddle will do more than just fill in a blank in a textbook. It will redefine the very nature of reality. A confirmed detection of dark matter particles would be like discovering a new continent on the map of physics. It would not just be one more entry in the particle zoo. It would be the first tangible piece of an entirely new kingdom of matter, a hidden sector operating by rules we are only beginning to glimpse. This discovery would instantly open a direct portal into that realm, giving us the key to a unified theory that could finally weave together gravity with the other fundamental forces. Our entire concept of what the universe is made of would transform overnight, shifting from a cosmos dominated by the familiar to one ruled by the invisible. The technological possibilities are staggering. Who knows what new principles we might uncover, what energies we might learn to harness when we finally understand the substance that forms the cosmic scaffolding of everything. The path of modified gravity leads to a revolution just as profound. To prove that Newton and Einstein were subtly wrong on galactic scales would be a paradigm shift of historic proportions. It would be the most significant rewrite of the laws of physics in a century, a fundamental alteration of our understanding of space, time, and inertia. Textbooks would become obsolete, and our most basic assumptions about motion would need to be re-examined. The very fabric of spacetime would have properties we never imagined, a subtle grain that only reveals itself in the faint gravitational fields of spinning galaxies. This would not merely adjust a few equations, it would change our philosophical conception of how the universe actually works at its most fundamental level. Regardless of which path proves correct, the repercussions will cascade through every field of physical science. Cosmology would gain a definitive framework for the universe's birth and evolution. Astrophysics would finally understand the true mechanics of galaxy formation. The solution acts as a key, one that will unlock a deeper layer of physical reality hidden beneath the phenomena we currently observe. This is not the end of a mystery, but the beginning of an entirely new era of inquiry, setting the course for scientific discovery for the next 100 years. The answer, when it comes, will not just tell us why galaxies spin. It will reveal what we are all truly made of and what rules the cosmos truly obeys. The mystery of rotating galaxies that should not spin that way remains a monumental challenge, a puzzle where observation and theory collide. Our journey has taken us from Vera Rubin's meticulous charts to the digital universes born inside supercomputers, weighing the ghostly presence of dark matter against the radical rewrite of gravity itself. This enduring enigma is a powerful testament to a simple truth. The cosmos is far stranger and more wondrous than we could ever imagine from our small corner of it. It pushes our technology to its absolute limits, demands unprecedented collaboration across scientific fields, and stretches the very fabric of human thought. The final answer is not yet written, but the pursuit itself has already transformed our cosmic perspective. With every new observation, every subtle signal from a detector deep underground, and every daring new theory, we move one step closer to unveiling one of nature's most profound secrets. This great detective story is far from over, and now you are a part of it. We would love to hear your thoughts on this cosmic mystery in the comments below. And if you are ready for the next exploration into the unknown, subscribe to join us on the journey.